introduce you Professor Othman. Professor Othman Bouhali, who is a research professor and the director of research computing at Texas A&M University at Qatar. He is the founder and director of the TAMUC, Advanced Scientific Computer Group. His main work is on computational physics, Monte Carlo simulation, and high-performance computing. Before he joined TAMUC, he was given the responsibility of computing group at the High Energy Physics Institute of Brussels. His research focused on the scientific grid computing, in particular the optimization and application on the grid infrastructure for intensive scientific application. Currently involved in several projects on medical physics, three-dimensional scientific visualization, distributed computing, and image analysis techniques. Once again, thanks, Professor Othman. You have 45 minutes, and you have also the floor. The floor is yours.
Okay. Good morning, good afternoon, Assalamu alaikum. Can you hear me?
Yes.
Okay. First, I would like to thank the organizers for inviting me to give this talk. So my name is Othman Bouhali. Actually, I work at Texas A&M University in Qatar, and Texas A&M University in Qatar is a branch campus of Texas A&M University in the main campus. So we have been here for now 17 years. We are an engineering school, but we also do a lot of science, math, and physics research. And in addition to that, do petroleum, chemical, electrical, and mechanical engineering. So today I'm going to present our activities, especially in our group, mostly on modeling and artificial intelligence applications in imaging and medical physics activities. So I will start by trying to give you a summary of what I'm going to say. So we'll try to introduce you to the field of modeling, what we are doing, mostly in imaging and treatment of cancer. And I will also highlight some artificial intelligence-based applications. And then I'll try to summarize and talk about some future work. So today, the talk might be a little bit technical, so I will go slowly, and I will try also to explain the terminology in the medical field. So let me just see. Okay. So let me start by one of the applications where we are heavily working on, which is the positron emission tomography. Positron emission tomography is an imaging technique that is used mostly for oncology, neuroimaging, and cardio imaging. And it consists of administrating a radio tracer, radioisotope, into the patient. So this radio tracer, for example, sodium 22, this radio tracer, it will emit a positron. A positron is a particle that has exactly the same mass as the electron, but it has a positive charge. So it's an antimatter. So this positron, when it is released in the body, it will interact with the molecules, it will lose its kinetic energy and will stop, and then it will meet another electron from the molecule of the body, of the tissue, and then they will both annihilate by emitting two photons side to side, collinear with 180 degrees, as you can see here. And those photons, each one of them will have 511 keV energy. So the most important thing here is that this means that if I can place a detector around the patient, this detector can detect the two photons and can measure the angle, which is 180, and then it can extrapolate the position where this annihilation took place. Now, why this is very important? Well, this is very important because if you take this radio tracer and you mix it with sugar, for example, we know that malignant tissues, cancer cells, will eat a lot of energy, will consume a lot of energy, which means will consume a lot of sugar. Now, if you detect all these photons, if you have a detector, three-dimensional detector, and you detect all these photons, you can see that there will be a very high spot here. For example, this is what you see in this image. So those high spot means that those areas are consuming sugar in a non-normal way, abnormal way. So this means there is something wrong in this area of the body. So again, as I mentioned, by putting a sophisticated detector, detecting coincident photons, two photons, and you can easily reconstruct. Now, what you want to do is the detector that we are using is composed of a block of scintillation crystals. A scintillation crystal is a crystal, whenever it is hit by a photon, by light, it will generate another light, and this light can be collected and then can be processed by a computer and by an imaging processing algorithm, and then it will give us a topology of the body. So as I mentioned, the positron emission tomography, which is PET, has an application in cardiac imaging, neuroimaging, and oncology, and there are also other applications, but those are the main three areas of this positron emission tomography. Now, the element of a PET scanner is a very expensive scanner. It has a system that detects those photons, which is mostly the crystals that I talked about. It is also composed of a very sophisticated data acquisition system. And as I mentioned, we need to reconstruct the image in order to see where this tumor or where this abnormal cells or region is located. And because we are talking about very large systems, we are also talking about mechanical and electronic design that has to be optimized. So obviously this requires a lot of modeling. And also recently, in the past few years, the AI, artificial intelligence, has been introduced in the subject. So I'm going to show you some of our results that we have done recently. So what we are doing, we are conducting a full chain of simulation, starting from simulating the crystals, to simulating the dose that is administered to patient, simulating the annihilation of these positrons that are emitted by the radio tracer and annihilating with the electrons inside the body, and then simulating all the signals that are generated until we get the final, and of course, reconstructing the image until we get the final result. So this is just an interface that we are using and we have developed with our developers colleagues that we published here. So here you can see small crystals that I talked about. Those are collections of crystals, and each crystal will give us a signal if it is hit by a photon. And as I can see, this is an interface that we developed, and you can see that the interface has here, for example, 4 rings of crystal, and there is a phantom inside. Phantom is just like a source that will give us photons, and we will be able to detect it. So the software that we have worked on, you can see we have done this simulation, the red part in this table, and you can see we simulated most of the PET scanners that exist in the market, and you can see that our simulations match very well with the experimental measurement that have been done in place physically on those PET scanners, whether the scanners from Siemens, from Philips, or from GE, General Electronics, etc. Again, this is a work that has been published recently. So we have been able to perform a large-scale simulation of the whole process. And then this enabled us to go and look for even additional devices. And this is what we have done recently. So actually we invented a new device for in nuclear medicine. And this new device is tackling a very big problem in nuclear medicine. In fact, when you inject the tracer, radio tracer to the patient, what you see is that you need to localize the or to measure the blood time activity, because remember, when you inject the radio tracer, this radio tracer will take time to spread in the body. So you need to measure what we call the blood time activity in order to localize the maximum the time at which the activity is at its maximum. This is where, at the moment when you have to take the images in the scanner. So how do we do this blood time activity until now? Is actually by taking a blood extraction. So basically by extracting blood from the patient every 5 minutes. And this is very, very uncomfortable for patients, especially patients who have phobia from the blood, from the needles, etc. So what we did, we came up with the idea of a non-invasive arterial blood radioactivity device. So we invented a device that can be placed just around the wrist, okay? And this device will just detect the radiation and will detect those simultaneous photons from the radio tracer, and it will give us this activity plot, time activity plot. And in fact, to do this, we had to do a complete simulation, starting from the simulation of the wrist itself. Here, for example, I am showing you a picture from what is in our wrist, all of our wrist, and you can see the radial artery, the radial vein, the ulnar vein, etc. So this is what it did exactly. We simulated the complete arterial wrist. And you can see here the simulation model takes the tissue, which is in orange, the bone in gray, artery, and the vein in red and blue. So this is what we did. And then we modeled the device that will detect the radiation emitted from the radio tracer that was injected into the body. And you can see we were able to measure and to detect through the simulation and to prove the concept that this detector or this new device can easily measure the blood activity, time activity curve. And in fact, this is what a paper. This is a publication that we recently published. But this device has also got a US patent recently, and it also got 3 provisional patents, which are also under process, because we are also improving the design, and it got the attention of some US companies for the moment. So this is what we can do with the modeling. It's not only classical modeling, but you can even invent new devices. Now, this is for the modeling. For artificial intelligence, we are also working in many areas, including the fact that the positron emission tomography is a very fast modality, but it has a limiting factor, which is the spatial resolution. And this is because of the size of the clusters. So you need, the crystals. As I mentioned, you need the crystal thick enough to absorb the photon. So this will give you high efficiency. But if the crystal is thick, then you will lose in resolution, because then you can, at crystal of 3 millimeter by 3 millimeter by 3 millimeters, you can only say that our photon is localized within a 3 cubic millimeter volume, which is low. So spatial resolution is very, very important, because this is the one that will give us where the tumor is localized. So we need to go to less than 1 millimeter. And this is what we are doing, and with the other collaboration, is to look at the depth of interaction. So we want to know, even inside this 3 by 3 by 3 millimeters crystal, we would like to see where exactly the photon has hit. And for that, you can only do it through artificial intelligence and training the models. So I can show you here, for example, if you have the real hit of the photon in this bottom plot. But then if you assume that your interaction happened in another point, you can easily see that you have a mismatch and you are not able to identify the tumor with a precise. You are committing a mistake, an error in the spatial resolution. So the idea here is to conduct experimental measurement by shooting crystals by photons, and at the same time conduct large-scale Monte Carlo simulation in order to train the model. Whenever there is a specific topology, then this model will tell us that, yes, the depth of interaction is at this point. And this is based on a convolutional neural network that has been applied for this depth of interaction. And the model has been trained both on experimental and Monte Carlo data. And you can see that the model has been very successful in obtaining 99% of efficiency and also 99% of accuracy, accurate localization of the depth of interaction. This is very important because if this model now is integrated in PET machines, it will lead to a very good resolution, which will improve the performance of the PET machines. So this is what we are doing in positron emission tomography, which is, as I mentioned, it is an imaging technique. Now, we are also going further with our collaborators in US and also in Ghent. In fact, most of the time until now, the PET machines are small PET machines that can image only part of the body. And you can see from these statistics that this is only 1 or 2% of the emitted signal is detected in a classical PET. This is because when you administer the radio tracer to the body, the radio tracer is spread over the whole body. Of course, it gets concentrated in tumor cells, but it's still getting into the kidney, into the liver, into other bodies. So in fact, in case of other issues like other tumors, metastases or something like that, you are unable to detect this with one single layer like that. So what we are proposing is not only to build one small PET, but to build a full body PET. This is what you see here in red. So it's 104 centimeters. And this has been, we have been working in this in the past 3-4 years. We have very good publications and also presentations at international conferences. So this is how it works. So instead of having this small PET, we are going to a larger PET, and we are even going to a PET that can be adapted to children and can be adapted to obese people. So this is a very, very challenging design we are working on. But well, yeah, and actually this is just to give you an idea of the model that we are building. Now, and again, this has been presented last year in the IEEE imaging conference. Now, the challenge here with this total body PET, remember, you have a total body machine that will image the whole body, which means you will have radioactivity coming from all the body. This is very, very challenging in image reconstruction. We have been working in the past 6 months just for this image reconstruction, because you are not reconstructing the images from the brain or from the kidney. No, you are reconstructing all radioactivity that are coming from all sides of the body. So in order to reduce the noise, we are discussing and applying deep learning. And in order also to cope with the large number of events, as I mentioned, we are also applying convolutional neural network. So this is something that we are working, and we are in the process of publishing new results. Okay. Then another area, this is the positron emission tomography. Another area is the CT and cone beam CT. CT is another imaging modality. it consists of emitting photons, like when you go and take a chest X-ray. So this is something similar, but with high dose. And again, here, what we are doing is working with the hospital here. We have been able to model the whole CT machine. And you can see here, so the CT machine works as the following. You have an electron beam that is accelerated. This electron beam will hit a target that is here. And this target, because this electron beam will hit a target, it will be subject to what we call in physics Bremsstrahlung. So in French, rayonnement de freinage. And then this will emit photons, and those are the photons that are used to image the body. So we have been able to to model the whole bunch of this CT and compute very important parameters that are used normally to assess the efficiency, accuracy of the CT scan. And I can show you, for example, here, those are our results of generating the X-ray tube. Remember, we accelerate the electrons and then we get the Bremsstrahlung X-ray. And here, the red is our simulation and the blue is the exact calculation from the quantum mechanics, and you can see it's perfect as a calculation versus simulation. And then we went ahead and we measured phantoms, full body phantoms and head and neck phantoms at the hospital, and we compared our simulation to it, and it just getting perfect result. So this has been presented 2 times, 2019, 2020 at the European Congress of Radiology. Then, now that we are able to do this, we can go further and start applying artificial intelligence in CT in order to do a dose calculation and dose optimization. And in fact, what is happening here is that we are trying to combine Monte Carlo modeling that we are doing and convolutional CNN, or convolutional neural network, in order to minimize the dose administered, the radiation dose administered to the patient. Now, the idea here is, can we go from, let's say we image the patient with a low dose, but with a large number of images. Can we aggregate those low dose, low resolution images and aggregate them and produce a CNN algorithm that is trained on those low dose, low resolution images to produce a high resolution image? And this will avoid high dose administered to the patient, because remember, patients can be vulnerable, can be old patient, or can be also children. So this is a work that we have now, we are working on. In addition to that, we were able to assess the staff safety. Remember, when you are a nurse in a hospital, every day you are exposing yourself to radiation. So what we are doing here, we have produced a tool for the hospital to do the simulation, and we were able to identify a hotspot for safety assessments. So in a room where the CT and the cone beam CT is operated, we can tell the hospital that those areas of hotspot, those are really the areas you have to avoid when you are operating the machine, because those areas, they suffer from what we call X-ray scattered photons. Okay, so this is for imaging. So remember, a process in oncology starts from imaging, which will identify the tumors or abnormal tissues, and then you go to the treatment. Treatment of cancer can be 3 types, or can be combined: surgery, can be chemotherapy, and can be radiation therapy, killing the tumor by photons. For the radiation therapy, we are doing, again, a full Monte Carlo simulation. So so here what you can see, So we are generating a photon beam of 6 MeV, mega electron volt, and then by applying, actually we are modeling exactly the same variant clinic module that is also installed in several hospitals in Morocco. And then we are doing the full modeling of the device and testing our simulation. We compare our simulation to measurements taken in water tanks, phantoms at hospitals, whether in Morocco or here. So, so we are involving all the physics process that you can think about. Remember, when a photon is traveling into the body, it will encounter several processes, including photoelectric effect, Compton scattering, Rayleigh scattering, per production, etc., etc. So we calculate two important parameters in radiation therapy, which is the percentage depth dose and the dose profile. This is the percentage dose, depth dose is how the photon beam is losing its energy as a function of the depth inside the body. And again, an important thing here is that this simulation is taking a huge amount of time. So we were able to minimize the simulation time from 2,400 hours for one job to 15 hours. So, and this is thanks to parallelizing our code and running it in a supercomputer of 5,000 cores and with 1 petabyte of disk space. Again, as I mentioned, we are comparing our measurement, our simulation to the measurement taken in a water phantom, and you can see that the measurement and the experimental measurement and the simulation are very good shape, in very good shape compared to each other. And again, this has been presented last year in a conference in London. And at the same time, we are now, we have embarked on a very, very ambitious project by combining Monte Carlo and existing data, so that we also combining complementary modality, for example, PET, CT, X-ray, etc., combining all of them in order to provide a comprehensive picture of the body. And this will help us to get more information about the cells, about the disease, about the tumor, and this will help us improve the dose delivered to patients. The reason why is that it has been, it's a confidential project, but it has been demonstrated that radiation therapy, if it is not well taken into account, it affects certain organs, critical organs and sensitive organs in the body. So our goal here is to avoid or to minimize the dose administered to the patient, but keeping the same efficiency. And this will be done, and it's being done. We are working on it using artificial intelligence in radiation therapy. So this is for the moment what we are doing in our project. Now, on the other hand, as I mentioned at the beginning, the first part of my talk was artificial intelligence and modeling in the field of imaging and treatment. Now we also have groups working on artificial intelligence for e-health. And I will give two examples here. So here, together with a group in Qatar Computing Research Institute, had been working on a non-invasive pre-diabetes risk score for Qatari population. And in fact, what is happening here is we would like to provide a tool to everyone. So this tool, just by providing certain information to the tool as a normal person, this tool will tell you, okay, you have, what is the risk that you will become diabetes person? And what is the risk that after 5-10 years that you will become diabetes person? So this is done by getting data from the Qatar Biobank project. Qatar Biobank project is a project that has been established in the past 5-6 years. And the idea is to conduct blood samples, a storage of blood samples and imaging from let's say 100,000 populations. And this will help us if we are getting the data, which we are doing now. If we get the data, we will be able to apply AI techniques on this data and other techniques in order to infer the behavior and any other type of diseases that we might have. So here we got around 8,000 subject data from 8,000 confidential subject, anonymous subject, and 4,000 were, or 5,000, around 5,000 were taken as control samples, and 2,300 pre-diabetes, and we divided them in two sets, training and validation set. And then we also applied several algorithms, deep learning, XGB, random forest, etc. And then here there is a website now where everyone can connect to this website, and by answering 5 questions, the website will tell you the risk score that you might become diabetes. And the next step now is going and integrating this in a hospital in one of the cities here in Qatar, and as part of the diabetes smart clinic. And this is now becoming a web application that will be soon downloadable from different iOS. Okay, so this is one area. And other area, so as I mentioned previously, AI for health, the first part is about software, and another part here is about hardware. And here the idea is to develop a wearable device that can detect and prevent hypoglycemic events. So basically, this device will detect some abnormal variation in your blood heartbeat, in your heartbeat, in your temperature, in several areas. So it will be trained based on AI techniques, mostly machine learning pattern detection. And this will give you an idea, or it will warn you, the device will warn you about, be careful, you have symptoms that you might become diabetes, or that you might have hypoglycemia. So again, this is a project that is ongoing. And recently, a group here have worked with a hospital here for AI-guided aesthetic surgery. And here they have been able to help the surgeons in 2 areas. The cleft lip syndrome, you can see from the left side, this is the baby with this cleft lip disease. And by applying several AI techniques to other images of babies, they could reconstruct an image, and they could guide the surgeon during the surgery. And the same thing here for the Treacher-Collins syndrome. You can see the difference between the left and the right. So this is all what I wanted to say. There are, as a summary, the field of modeling in the medical field has been extensively tackled, but it has been also, it is under huge development now, especially because we have a lot of data, and we have also a lot of computing power that was not accessible, let's say, 10 years ago. In addition to that, the application of artificial intelligence in the medical field is booming. You can easily see that the number of articles are exponentially increasing since 2014, 2015. And so there is plenty of room for improvement and new applications in all areas of medicine. I only talked about 2, but it's a huge area. And there is still an issue of accessing the data. And the issues can be ethical issue, the ownership, who is owning the data, and confidentiality. So again, this is another topic of study that we have a project on it, but I don't want to talk about it, is how to tackle the issue of accessing the data. And yeah, so for that, I would like first also to thank the organizers, and I also would like to thank the audience for their attention. And I would like to thank my team members who have been very, very active in doing and supporting this research, and also the funding agency. Most of these projects that I showed are supported by the Qatar National Research Fund. Thank you very much.
Thank you. Thank you, Professor Othman Bouhali. I see the chat. While waiting for questions from the audience, I have maybe a question. It's a classical question. In the 18, artificial intelligence was a promising technology, and namely maybe the expert system which aimed to solve medical problems, education, and so on. And nowadays, everybody talk about artificial intelligence, scientists, but also politicians. Do you think that it is only a wave, or do you think that's it's a field that will still in some next decade? Because in your summary you talk about intelligence, artificial intelligence in medical field is booming. My question is will still booming in next years?
Okay. Yes. So I think the answer is twofold. First, yes, the artificial intelligence is booming because for one single reason is in the past 5-6 years it has been shown that it gave very good result. And you can see that there is, I don't have to, but if you search in the internet, there is a Harvard group, a group from Harvard that I know very well. They had a competition where AI algorithm bet the surgeons. Yeah, so there is a need, and it is booming because we have the data. We have access to, well, we have the data. We have huge amount of data that no one will be able to analyze on its own. So when you have, let's see what is happening now in COVID-19. COVID-19 now, most of the research that is being done is based on acquiring the data and trying to find how we can detect COVID-19. Now, I want also to, the reason why AI is booming is because it has been successful. And again, I give you an example of COVID-19. I think 2 months ago, MIT, which I work with them very well, MIT has announced, the group of artificial intelligence, CSAIL group, has announced that they produced an algorithm that just by coughing, when you cough, it will detect 100%, until now, 100% whether you have COVID-19 or just normal cough. And it has been tested. And I think you can even get an example, you can test it online. So yes, when you tell this to the politicians, to some of the doctors, they said, yes, it's very good to have such tools. So this is one thing. The second thing, as I mentioned, we have the data. Now, the other thing is, again, we don't want also to overpromise. So artificial intelligence will not solve all the problems, will never solve all the problems, for one single reason. A human subject is a very, very complicated, and you cannot control it only by algorithms. Yeah, so you still need people, you still need, but you cannot do this in one automatic way. So you have to balance. Maybe it is a wave. It is a wave because the reason why it is becoming a wave, it's because politicians are talking about it too much. Now, it doesn't mean that it's useless. No, you have seen what happened in 2016 in the US presidential elections with the group Analytica. And you can see also that recently there has been even a football team, a soccer team, that has been suspect that they are using AI. So for example, you have a match next week with the team number X. Okay, so you will go, there is they developed, it seems a company developed a software that can look at all the video of team X, and they will tell you what are the weaknesses of team X. So yeah, so AI can be applied in many areas, but we don't need to overpromise. That's my answer.
Okay, thank you. I don't see questions. I see that many audience, many people, thanks you very much for this useful presentation, useful links also.
Yeah, I mean, look, there is here, I have several researchers from Morocco. I have several students also collaborating with me from Morocco. So I'm trying also to help the young generation here. If anyone is motivated to start a research project or some ideas, we can, or professors in Morocco, I mean, we can actually, we are preparing 2 projects for this call, the call that is ongoing now, I think in yeah.
Okay, thank you very much, Dr. Aguari, for your excellent presentation. I have maybe one question about artificial intelligence in e-health.
Yes.
That artificial can replace a doctor, for example, in medicine.
Sorry, I could not understand the question. So I know that you are talking about the e-health application. Which one?
Do you think that artificial intelligence can replace a doctor in
We don't hear you, Mustafa.
Honestly, I can't understand because I think you are far from the micro. Yeah.
Yes. If you can change the micro, or maybe move to your PC.
And now, Dr. Bouhali?
Very
Perfect.
Good. Go ahead.
Okay. My question about artificial intelligence in e-health.
Yeah.
Do you think that artificial intelligence can replace the doctor in the medicine?
It cannot. This is a very interesting question, and this has been a lot of debate. Personally, nothing can replace a human. Nothing. We are over promising, and this is of course, politicians, they like this because they are always looking at the budget, but and when they get sick, they go to Europe or US to get no, but no. The reality is that you can never replace a human. now there is a new term that has been in the past 2-3 years has been used. It's collaboration human AI. So we need to collaborate with AI, with artificial intelligence. We don't need to see it as a threat. We need to see it as a tool that helps us in our tasks.
Okay, as CAD.
Okay, Dr. Bouali. I hope we can continue our cooperation with you and our PhD student for the next year, inshallah.
Inshallah.
Okay, thank you, Mustafa.
Thank you very much.
Thank you, Mustafa. I have question, Professor Bouali. Maybe you talk about, because we have enough time, I think. You talk about parallelizing the code.
Yeah.
Which tool do you use?
Well, it depends. Okay, so it depends. Of course, when you want to parallelize the code, you have to proceed to a profiling and see where. I mean, some of the processes or the steps cannot be parallelized. Some of the steps can be parallelized. So, and then you decide whether you want a shared memory, non-shared memory, and whether you want to go for MPI or OpenMP, etc. So that it's a classical.
Yes, because we talk about and I want to know what your idea about it. When this is talked about, it's said about from a specialist, it's better, you know.
Yeah, I mean, look, I have been working with I'm still working with the European Organization for Nuclear Research, CERN, in Geneva since 1994. The last 5 years, we had a code where we used to do detector simulation, mostly silicon detector simulation, etc. So, but this code is very useful, but it has been very slow. If you want to simulate a detector, it will take 3 days for a real simulation. So together with one of my software engineers, who is here in the middle, Ali, we were discussing, and I told him, look, we have this problem. So after 1 week, he did the profiling, and he identified 2 things. We can do the parallelization, but there is a process we cannot parallelize, but in fact, we can optimize. And then we introduce an optimization, and we got a speed up factor of 25 times. So which means we reduced the execution time by a factor of 25. And we published 2 papers, 2016, 2018, and now the software is available at the CERN repository. I mean, not the paper, the code is available. So sometimes you need to do this very, very deep profiling, and you need a good software engineer who understand, and it just get the work done.
Okay. Do you work in collaboration with the industry, and did you compare your development, what is done is with the current technology?
Well, in the medical field, yes, we are collaborating with industry. We are collaborating also even with the oil and gas industry for projects in safety. I mean, the work I talked here is, I can tell you, is 10% of the work that I'm doing. So we have a big project, a big group in augmented reality, virtual reality, and this again, we have some patent there. I have another group on augmented reality and virtual reality.
Okay. Thank you very much.
Thank you very much.
Thank you. I don't see any question in the chat. I would like to thank you very much.
Thank you very much. Have a nice day. And I'm chairing a session in 15 minutes. So
Okay.
yeah,
Okay. Good luck.
thank you. Thank you.